Kia ora, good morning everyone. My name is Bernd Krauskopf. It's my pleasure to introduce the first plenary today by Priya Subramanian. Maybe we can already get the slide up. Yeah, there we go. And her talk will be about pattern formation, as you have read and can see over there. So let me just tell you a few brief words about Priya. She got a PhD in 2012 from IIT Madras in aerospace engineering. So she seems to be more down to earth these days, if you look at these pictures, but some is still high up, okay? And then she went to the Max Planck Institute for Dynamics and Self-Organization in 2012 to 15. She spent then 4 years in the University of Leeds, and then had a stint in Oxford from 2019 to 2021. And in fact, Oxford were very lucky because we made her an offer in April 2020, and it took 1.5 years for Priya actually to be able to come to New Zealand and take up her position for obvious reasons, I should say. And she got the full shebang of entering New Zealand during COVID times and so forth. So if you ever have any questions what that was like, Priya would also be the person to talk to. In any case, she has been with us since September 2021, and it's a great pleasure for me to ask her to deliver her talk. Thank you, Priya.
I'm on. I can move away from the desk if I want to. So, kia ora everybody, and I really want to start off by thanking the organizers for the opportunity to give a plenary talk. I didn't think this was in the cards for another 10, 15 years. And I pretty much thought, what should I talk about pattern formation, and decided that I'm going to talk about just a little bit of introduction of trying to model a pattern forming system, but then go on to talk about two different new connections with other branches of mathematics that I've been thinking about and pursuing for the last, let's say, 6 years with my collaborators, Andy Archer from Loughborough, Edgar Knobloch from Berkeley, Alistair Rutledge from Leeds, and Vanessa Robbins from ANU. 2 of the 4 are in this room, so if there are questions that are too technical for me, I'm going to get help. So yeah, with that, I want to start with looking at patterns that we can see in nature that span many, many scales, starting from kilometer length Kelvin-Helmholtz waves that we can see in clouds, to on the scale of a meter, patterns that we can see in animal patterning on their skin, to millimeter level honeycombs that bees build. And this is, it is looking fuzzy. It is supposed to look fuzzy. It's a scanning electron microscope view of a quasi-crystal. So this is a special type of pattern. It's much more complicated because it has one of those not allowed symmetries for something to repeat across scales. So it was not considered to be a crystal at the beginning, but those are some of the patterns that we can observe in nature. If we go away from nature and try to recreate very well-ordered patterns in a lab experiment, we always think about patterns as we have no patterns as being the flat state or the liquid state or the unpatterned state, and that state somehow loses stability and we start to get patterns. And the top 3 images are all from convection experiments at using different materials. And we can see that you can get patterns that are just straight lines. We call them rolls or stripes. We can also have a mixture of water and ethanol producing these kind of square patterns. And if you take some other kind of blend with silicon and oil, you can get hexagonal patterns. All of this in the same physical mechanism of convection. So that's interesting. The bottom 2 experiments are slightly different. Here we take a layer of something, either a fluid, in this case it's just water, and it's in a weird shaped, it's the shape of France. You just shake it up and down really vigorously at about 8 to 10 Gs, and at that level of acceleration, the layer of water stops being flat or unpatterned and starts to form patterns, very interesting patterns like this. If you notice here, if you think of this as the center, there is 12 pentagons surrounding it. That's also one of the hallmark of this not allowed or forbidden symmetries, because it's not something that's supposed to tile the plane or cover this domain without any defects. And there is a story about why it is the shape of France, and that has to do with English theoreticians and French experimentalists. Read it up, it's fun. The last experiment here is with granular media. We have small brass beads that are, again, being shaken up and down at high accelerations. And here we see that there is patterning, but this patterning is only happening at parts of the domain, not everywhere. And this pattern is now going to respond at half the frequency at which you shake. So the first half of the cycle, it's going to be a peak, and the next half, it's a trough. So it kind of has this kind of different responses. So some of the common features we can think about is the same system can form different patterns. That's interesting. What might be the thing that picks the pattern? We're going to talk about that. And they can be time varying or just steady. They could have multiple length scales, because to form this pattern, you need more than one length scale to be preferred. You can have spatial localization of the type here, which is much more complicated, but you can also have spatial localization in a steady pattern. And many of these patterns have a lot of symmetry, which has always been used to try and analyze them or to study them. Cool. So we're going to ask this question: how can we create a minimal model that forms this kind of pattern, spatiotemporal patterns, with a chosen periodicity? That's the only ingredient we're trying to take with us. We want the chosen wavelength or chosen length scale to be visible in the pattern that we create. So with that, we start with just designing a PDE, because we want it to be a spatiotemporal pattern. And let's consider the scalar, real scalar u, to be a function of space and time, and it's supposed to represent the pattern. You can think of it as density or temperature fluctuations above a mean, or you can think about velocity in a specific direction. So any of those would work here. And any PDE can be written as some linear and a nonlinear functional. The linear part is what we want to talk about first. So if we think, how can I solve just a linear part? You can write exponentials, one for space and one for time, and that is a form in which will satisfy the linear part of this PDE. And here we have two important parameters. The first one is the prefactor in the exponential for time. That tells us how fast any perturbation is going to grow in time. And this exponential of I to the ikx is called a mode. And this k is a vector depending on how many dimensions in space we have. So here we've chosen 2, x and y. So the L2 norm of that is what we call as a wave number. This is the length scale that we've picked. Oh, that is what picks the length scale. So different k values have different length scales. And there is a nice relation, which is the dispersion relation, which somehow rewrites the sigma as a function of this wave number k. And that is the one thing that we want to somehow design. Because if we can design that, we are making sure that the system that we write with that equation will pick patterns of the length scale we've chosen. So all we want to do is we determine the sigma of k and take the inverse Fourier transform. That'll give us the linear operator. So we're just going to try to design this dispersion relation. So the conditions we take here are reflection and rotation symmetry, which tells us that this dispersion relation should be an even function of this wave number. Okay, that's not telling us much except reducing the options that we have. Large and small length scales should be damped because we want one specific length scale to be picked. So anything larger than that or smaller than that, you want it to be damped. We can't say anything about the small length scales because k keeps on going to larger and larger values because length scales are inverse to the wave number. For the large length scale, you can at least say what happens at k equal to 0, and we choose that to be a parameter in our model, which is a negative value. And then finally, we have to choose this length scale. And that means we're saying this curve sigma of k has a maximum at that point. That means the first derivative goes to 0 and the value itself has some height. So those are the conditions. And this just gives us an even polynomial, and we have 3 additional constraints. So we choose a general 4th order polynomial, and we plug in these 3, and we rewrite the same expression, and we get it in terms of the height of the peak at k equal to 1 and this negative value at k equal to 0. These are 2 different values, so instead of writing r1 minus sigma naught, we can maybe write that as a new parameter, maybe m. So that's what we do here. And we now have a linear growth rate, R1, and this M is a prefactor for the spatial part of this dispersion relation. We want to plot how the sigma changes sign for different values of R1 and K, and that's what we see here. The blue line is where sigma is always 0, and that is the neutral stability curve. So that means any parameter combination of R1, if we take a negative value of R1, all of the wave numbers are having sigma less than 0, which means our flat state is still stable. As we increase R1 at some critical value here, which happens to be 0, we have the first time the blue curve we're crossing the blue curve, and that means at kc equal to 1 is the first wavelength that becomes unstable. That means the system will start to form patterns at that length scale. And because we have no length scale being chosen, and as we vary a parameter, one length scale being chosen at some critical value, we call this a pattern forming instability, because as you cross the instability, you're suddenly choosing to form a pattern that has a length scale that is designed. So that's pretty much what linear theory can tell us. All that linear theory then tells us is once we've crossed the instability, you're going to have exponential growth. So you need nonlinear terms to then tell us what happens to this pattern, whether it keeps growing and then saturates, or does it change into another pattern. So we need to definitely do a bit of assumptions about the nonlinear part. And here for the functional, we choose the simplest kind of nonlinearity we can think of, which is just polynomial. So it's just u squared and u cubed. That's what we have. We have a destabilizing quadratic nonlinearity, as in it kind of keeps pushing the pattern to grow. And we have a saturating cubic nonlinearity to keep things well-bounded, and instead of going to extremely large values. And this is now a prototypical pattern-forming system because we've only taken this ingredient that we want patterns at a given length scale and created this. So this is also known as the Swift-Homburg equation, and it was derived for describing thermal fluctuations around a phase transition. And because of the choice of the nonlinearity that we've done here, which has the squared and the cubic nonlinearity, this is also known sometimes as SH23. And one of the first things we can do after doing linear stability for a PDE is to simulate it. You put it in a box that's periodic in both sides. So the first row is showing you real space, the middle row is showing you the corresponding Fourier transform, and this is showing us the log to the base 10 of the norm of u. So this is just to indicate how things change as a function of time, but we're taking the collective norm over the entire domain as our metric. And we start from a very random, small amplitude initial condition, and the Fourier transform is also broad to reflect that. And as we move along in time at about 2,000 units of non-dimensional time, we're still kind of very small amplitude, 10 to the minus 4, but we've started to create patterns at a length scale. That might not be so prevalently or obvious from looking at the real space, but if you look at the Fourier space picture, you can clearly see that there is a circle that's chosen. The radius of that is the length scale that we've plugged into this model. And as we move along here, this line is pretty constant slope, and the slope of this line is our growth rate. It should be about 0.001, so we're just crossing this instability threshold. And as the amplitudes get bigger, at some point, the quadratic nonlinearity gets switched on first. And that's what you see as the really straight shooting part up here. And we take an example of the pattern from there, and we see that we're already starting to form hexagons. There's just a little patch there. The amplitude is probably already reached the maximum that it's going to reach at some of the peaks, but not all of them. And the rest of the domain is still needing to be filled. The Fourier transform clearly shows the breakup of this circle into 6 little peaks. And further on, when the cubic nonlinearity comes in and saturates, you get after a very long time, you get all defects and other things are gone, you get a perfect hexagon, and the hexagon does have 6 little black dots on the circle still. So we've kind of made a model that can form patterns at the length scale that we want. We've chosen it to be non-dimensionally 1, but that's fine. Okay. What is the other thing that we've seen in some of those pattern-forming systems is that you can get more complicated patterns like the ones that you see here. These are two different patterns observed again for the Faraday wave system when you're shaking the water up and down. And this cannot be explained with just one length scale, because the Fourier transforms of both these patterns, this is a dodecagonal quasicrystal. If you think of this as the center and you count the number of peaks around it at the same length, you'd find that there are about 12. That might be hard to do, but you can also count how many peaks are there at the solid circle. And there are also an equal number of 12 peaks on the dashed circle. They are a bit gray and are harder to see. And that is definitely showing us that there is two different length scales that this pattern likes to form patterns with. So it uses both of them sometimes, one of them sometimes, and so on. So the same system also shows this kind of pattern, which seems a lot more regular, right? There is patches of hexagon in clumps of 3, and they themselves are arranged hexagonally. These are called superlattice patterns. This specific one is a superhexagon. And if you look at the Fourier transform of it, it again shows these two length scales. And here, notice that the second length scale, the dashed circle, is much, much smaller than the solid circle. In fact, the radius of the inner circle is less than half of the outer circle. And in that case, what happens is vector additions of these wave vectors can only happen one way. Two of the long wave vectors can add up to give you a small one. That's the one that's shown there. But the reverse way of transmitting energy back to the larger circle doesn't happen, which it does happen here. So it's much more nonlinearly interacting when you have q's, or the ratio of these length scale, that's what is called as a little q, is greater than a half. So these kind of patterns seems to suggest that we need two length scales in our pattern. And we can extend the model that we have, and that's kind of where Lifshitz and Petrick started. And they basically said, if this C was written as M in our notation before, we had this as our spatial part of the dispersion of the linear operator, which now they added another factor at another wavelength Q. So you'd have two different length scales. But one of the things to note here is both of them would become unstable at the same R1 that we have here. So that's not necessarily an independent way of doing this. Rather, if you have two length scales in your system, it's better that both of them are free and independent to become unstable by themselves. So if you want to do that, we again want to write a PDE model like this, and we're going to again design an L like this. And that amounts to, again, choosing choices, getting conditions, and plugging them together in a general nth order polynomial, and you get a nasty-looking expression. But pretty much kind of a start from the conditions and get to a dispersion relation. That's exactly what we did in the last example as well. And the Fourier and the full nonlinear simulations of this also shows that you are able to go from a random initial condition to a system with definitely 12 peaks on the blue circle and 6 peaks on the red circle, which is a super hexagonal pattern. It looks slightly different, looks like stars, but that's kind of what we see here. So what we've done so far is we've said, okay, all it amounts to actually create a model is to design our dispersion relation. And if we can do that and choose a simple nonlinearity, we can at least study what this pattern forming system is capable of, right? And beyond the instability threshold, we definitely talked about how nonlinear terms become important. And so the question is, what can we do? What can we do with pen and paper or a little bit of analysis to say what are the nonlinear effects beyond the pattern forming threshold? And for that, we go back to studying the Swift-Holmberg equation, but we'll take the simplest case, one-dimensional Swift-Holmberg equation over an interval of 2 pi with periodic boundary conditions. So our Laplacian just becomes the second derivative along x. But the rest of the equation is pretty much the same. And we want to understand that we are in the neighborhood of this instability. That means in the neighborhood of the instability, the pattern's amplitude will be very small because it's just growing away from the flat state, which is what we call 0. And when we are growing away, we saw from the numerical simulations that things take a long time to grow because our growth rate in time is a very small positive number. So time would also be very slowly evolving, and we are very close to the onset. These are the 3 conditions that we want to plug into the equation and try to say something. So we rewrite those small amplitude by expanding our state variable u in terms of a small parameter epsilon in different orders. And we also now say that time flows slower with this small parameter epsilon to the power m in front of it, but we don't know what m is. We don't want it to be epsilon to the power 1 because we're not sure whether the scaling of the state variable and the time is going at the same rate. We don't know that. And to be close to our onset, we take our critical value and then we say the correction to it is also very small, but it's a different small number, epsilon to the power n. We have to determine m and n. They necessarily have to be positive, but other than that, we don't know anything about them. And what we do is we plug in these things into our PDE, and it looks a bit messy, right? So what we're going to do is to collect terms of equal order in epsilon, and we're going to try and solve at each order the equation that we get, and we're going to keep going till we get to a natural place to stop. I'll talk about that. The first order epsilon equation, we get no time derivative term. We only get the spatial part of the linear operator operating on u1 with a negative sign. And that you can solve using Fourier transforms and assume that you have a wave, e to the ix and e to the minus ix. They necessarily will have complex conjugate amplitudes, z and z bar, because we want u to be real. So we do that. And then next order, we have a same operator on u2, and the right-hand side has u1, but we know u1 because we've solved it. We can plug in, and we see that we get this solution for u2. The thing to note here is that the contributions here are e to the ix and e to the minus ix, and here we get the k equal to 0, k equal to +2, and -2. So at every order when we've solved it, we are also assuming that all contributions at that wave number are already included. So we cannot have any more contributions at e to the ix. So keeping that in mind, we go to the order epsilon cubed, and this is where we say, okay, for the first time at order epsilon cubed, I get the largest nonlinearity in the model coming into this equation. We get the u1 cubed term for the first time. So we're saying we want to balance the nonlinearity, the parameter, and the time variation. And if you were to choose that way, m and n need to have values of 2, which is what we do. And then we say, oh, but this is now an evolution equation for u1, and it has this u3 that I don't know, but it also has just a u1 term. So u1 alone will have an e to the ix contribution in it. But we've already assumed that that has been accounted for when we did the balance at the order epsilon. So we need to take the component of e to the ix from this equation and say that that has to be equal to 0. So that gives us an equation, now an ordinary differential equation for how the amplitude of u1 changes as a function of time. We started with the PDE, we did this expansion and collected terms at different orders, and we ended up with an ODE. And this is the Landau equation. Most often we'll end up with normal forms of bifurcations with the symmetries of the problem that we have here. It's a pitchfork bifurcation with rotation symmetry. And other problems may need different scalings, but in almost all cases we want to do this balance. Nonlinearity, time, and parameter. And there are other ways to call the same procedure. You can use, for the singular operator, you can use a Fredholm's alternative, and in that case, this equation is then the solvability condition. So, but the point is we're always starting with PDEs and ending up with ODEs, which we want to solve the amplitude of Z, which means that we want to have equilibria for this ODE. That means we just have a cubic polynomial on the right-hand side that we want to solve. That we can do by pen and paper. This one's even easier because one of the solutions is 0. Then we have a plus or minus quadratic solution for the amplitudes of Z. Great. But in 2D and 3D, for complicated patterns, you have way many more wave vectors that you have to consider. So in 2D, you have, for dodecagonal symmetry, you have 12 vectors in a circle, and we know that there are 2 circles in this quasi-crystal pattern that we want to understand, so 24 coupled ordinary differential equations, each having tilde cubic term, right? And that's what we want to find equilibria for. And in 3D, you could get 30 edge vectors of an icosahedron. The white balls in this kind of made-up picture can be thought of as the ends of these vectors, and the central one is k equal to 0. And that will need to be expanded like this because there are two wavelengths again, and that gives us up to 60 coupled amplitude equations that we want to find the equilibria for. One of the first things we'll do is probably use numerical continuation, right, to solve for this. And numerical continuation is iterative, and it requires us to give a good guess. And most often we get good guesses by considering symmetry, right? So what if we want to consider reduced symmetry? And what if we don't want to give an initial guess at all, not use an iterative method? So that's kind of the first connection that I want to talk about, because the number of unknowns that we have with respect to different patterns can change as a function of how complex the pattern is. The flat and the stripes and the hexagons, they all have only 0 or 1 unknown. So you can do pen and paper. It's all just one cubic equation, or just the answer is 0. But if we go to different wavelength ratios, you can either get dodecagonal quasicrystals, which have 6 Zs and 6 Ws. That doesn't, we're assuming full symmetry, full dodecagonal symmetry. So we end up with just 2 coupled cubic equations of this type. We can also get more complicated ones with 2 or 3 or even 5 number of unknowns. These are reduced symmetry patterns, and direct solution is possible. If you want all solutions or even some of the solutions of this, you can write them both together as one 9th order polynomial. Find roots, right? That's a resolvent kind of method to try and approach it. But we can try to do something better and use homotopy from computational algebraic geometry. This is probably the one slide I'd want you to remember from the stock if you don't want to remember anything else, right? So what we're saying is, I want to find the roots of this equation. I notice that it is 2 coupled cubic equations for Z and W with constant coefficients, and I'm finding equilibria, which means I put the left-hand side to 0, and I'm really essentially asking, I want all the real finite solutions of these 2 coupled polynomials. So, because all the powers of Z and W are positive. And with that, we can try to start with a system that has the same number of solutions. We can take Z cubed minus 1 equals 0 and W cubed minus 1 equals 0. They have the same number of solutions, they're easy to find, and then you slowly track what happens to the solutions as you change the coefficients, and in a homotopy end up going to your target system, f of z. And we want this homotopy to have good properties, like you don't want this kind of blow up to infinity happening somewhere in the middle, and that is about smoothness and accessibility. We don't want this kind of singular endpoints to have happen somewhere in the middle, and we can kind of ensure this by using a random complex gamma into our homotopy formula. This is a probability 1 algorithm, and a lot of people in algebraic geometry have looked at this, worked on this, even made really nice, beautifully documented softwares for this, and there is quite a few of them that you can just take and use. So all you have to do is start with that system, and you will end up with all the solutions for this. Next question is, what happens when I change parameters, right? And at that point, the first starting system to the target system is the computation that takes a lot of effort, because you're really looking at parts that might diverge to infinity, you're looking at parts that might be singular, and so on. But once you've done one of these costly initial solve, and you've gotten to your target system for some value p naught, moving that to another value p is much easier calculation to do, and you can do many of them in parallel, and all that can happen is some of your complex solutions can turn real, and some of your real can become complex. That's it. So as long as you can keep track of that over the complex field, you can do this kind of parameter homotopies over parameter ranges very fastly. You can also identify regions with a given number of solutions by calculating what happens to the discriminant. And you can also ask questions like, how many real solutions do I have at this parameter range, which might be important for biological modeling to say, is there any other solution? So the good thing about this is that you will be able to get this kind of pictures where you see that the number of solutions that exist, non-trivial, non-flat solutions that exist, are given for a whole range of parameters, and we see that they kind of go from 0 to 2, 2 to 4, 4 to 6, and 6 to 8. So we're also noticing the parameters where the bifurcations happen. We have all solutions, which is an amazing thing to do without giving any guesses. We did assume the symmetry to do the amplitude equations, but that's about it. And, doing this in 3 dimensions, we can also get different reduced symmetries. This is the full icosahedral symmetry, and these are 3 different symmetry broken ones. And doing this, we might be able to even kind of motivate physicists to find this kind of packing, which have not been seen. They have seen periodic stackings of decagonal quasicrystals, but there is no experimental result yet of aperiodic stacking of a decagonal quasicrystal. That's interesting, that's nice. That's the second part of the talk, and I think I have about 2-3 minutes to do this. I did go slow, that's okay. How to characterize the zoos of patterns that we get. In 2D and 3D, we get a lot of spatially localized patterns that look like this, and just now we talked about how reducing symmetry gives us a whole bunch more patterns, and we can also get patterns with defects here. There are defects somewhere around here, but they become much more apparent if I subtract the full hexagon from this picture, and that's what we see here. And this now looks like there's variation in part of the domain while the rest of the domain is flat. This is a reason why we can think about states with defect as localized states and apply the machinery that has been developed to understand localization there. And all of this kind of, we need these patterns to be classified. We need to know how similar 2 patterns are with respect to different reference states. And mostly what we do is we look at Fourier transforms of patterns in 2D and 3D. In 3D, you take transforms along 3 directions. You can also do more interesting things like a Gabor transform, which is taking Fourier transform along specific directions and length scales. For example, this pattern has 2 defects here, but if I were to take the Gabor transform along 3 different directions, I don't even notice that there is a defect along some of the directions. So it's not always a given that your more complicated transforms allow us to characterize the patterns that we have accurately. And also, all the information in spectral space is local, whereas if we try to think about the topology and how this changes, which Catherine might talk about a little bit in the next talk. Yeah, so forget about that. All I want to think about is think of water filling a landscape from below. If you're crossing a minima, you're creating a 0-dimensional object. If you're crossing a maxima, you're deleting a 0-dimensional object. But across a saddle, 2 things can happen. So think of the x's here as saddles and the zeros as minima. When we connected across this saddle, we just changed from 2 0-dimensional objects to 1 0-dimensional object. But when we cross this final saddle, we suddenly create a dimension 1 circle there, a loop there. And we don't know which of this is going to happen, and that is essentially non-local information, and topology is needed to kind of keep that information. We have that information in the real pattern, but when we take the Fourier transform, that information is hidden in the very high order effects of this Fourier transform, maybe. So a much easier way to do this is to take topological data analysis of your images. And I think I'm going to just show you some results of how I do that. For example, if you have the extended hexagon, this is where you talk about what length scales are born at different, as you kind of sit on one peak and you expand out, you see the distances at which you start to see another peak and so on. Almost all length scales here are described by the distance between interpeaks that are along the line and across the line. That's it. So that's why we see most of the information clustered together in one point of this persistence diagram. And as we go to the localized states, we have definitely different scales being born at much larger values of length scales. I think I'm going to just go to the, I have done some calculations initially to understand what happens if we now compare, instead of the norm, a Wasserstein distance, or how different these persistence diagrams are. That's what I'm asking. How different is this diagram compared to this, or this diagram compared to this? And we're doing that as we continue along the solution branch. And we are able to get pictures that tell us more about the sharpness of the envelope and about the geometry if we were to do a signed Euclidean distance where we take a threshold of the pattern and then we do this kind of topological data analysis. Is there another slide? I don't think it's going past this. I think I had one more slide, Morgan. If there is, yes, thank you. So in summary, we can definitely derive minimal models for pattern formation by designing the desired dispersion relation. That's a cool way to start to think about designing a model. Homotopy methods allow to solve amplitude equations or Landau equations that we arrive at for reduced symmetry and get all solutions with no guesses. And so I would say this is a great tool that we should all use. And the final thing is when we have zoos of patterns in 2 and 3D patterns, we might need a different measure to characterize them rather than just a Fourier transform. Thank you. I've got 5 minutes. Sorry? Okay, because it tells me this.
Okay, thank you very much, Priya. Fantastic. We have time for questions, and we should have people around. Yes, Lauren there with the microphone. So who's the bravest today to ask the first question?
Lauren, there's... Yeah.
Oh, there we go.
Thanks for a very interesting talk. I was just wondering whether you also can take randomness into account. And some of your patterns were very regular globally, but in some other experimental data you had patches of regularity, but then other patches not.
Yes,
so.
yeah. Yes, definitely we can start from a random initial conditions, and unless we pick up parameters very carefully and wait for a long time, we do get patterns with defects. Sometimes I also start with an initial condition that's an imprint of a pattern, because I want to get to the perfect pattern faster. So yes, we can take into account randomness in the initial condition, but the dynamics themselves have no noise.
So the final pattern is deterministic always?
Sorry, the
final pattern is always deterministic?
I mean, it doesn't have to be perfect. It might be that you start from a random initial condition and you've started with 2 different patches of hexagons with different orientation. They might grow and then form a grain boundary, and then it's stuck. That does happen, yes. I haven't shown you such things, but yes.
Question over there.
Thanks for the talk. How much does this tell us about the physics of what's going on with the underlying water? Are the 2 length scales sort of physically realizable, or are they more mathematical construct?
Yes, definitely. Thank you for that question. I have more slides, Morgan. Sorry. Morgan? Sorry about that. My clicker doesn't work anymore. If you could go to the extra slides. We can think about a system like soft matter. That's the one, thank you. We think about systems like soft matter or polymers, and if we consider what happens to them as you lower the temperature, you can have icosahedral quasicrystal. That's why the little portion of this Fourier transform shows us this 5-fold symmetry. But the modeling of this can be done at different scales. You can start at the microscopic level, which has now Newton's equations or Langevin equation, and then you have actually equations that have noise in them. But you can approximate different aspects about this modeling and arrive at a mesoscale description, which is what the results that you've seen, or I can show you. But this system, depending on the interaction potential between 2 particles, can have 2 length scales that it picks at the same time. Yeah, that's one example, but yeah.
On one of your slides, you said that Q being the ratio of the 2 length scales, you ended up with different types of patterns,
yes.
Like superlast patterns when Q was less than half and quasi-patterns when Q was more than half.
Yeah.
Can anything be said about that critical parameter when Q equals to a half, or not much?
I mean, at Q equals half, it is part of the 2-way interaction. When Q is half, you can still do this wave vector addition both ways. So it becomes the class of the quasi-patterns already at Q equals half. So Q less than a half is the 1-way energy distribution, but half is already on the other side. Thank you.
Do we have more questions? Oh yeah, there are more questions also down here. Okay. Let's start at the back first. Thank you.
Thank you. I have a question about your homotopy methods. to what extent are the results sensitive to the particular structure of the homotopy relation you start with?
We don't even have to choose the start system. There are some of the softwares that will start with, it creates the initial start system by itself. So in that case, the answers are not specific to the start system or the specific homotopy that we've done. It's just as long as we make sure that we start with the start system that has the same number of solutions that we expect. And over the complex numbers, you get all of the finite solutions anyway as part of this answer. Yeah, was that what you asked, or? Okay, cool.
Thank you, Priya, for the lovely talk. I was just wondering, when you showed us the Fourier transform of the simulations with the multiple length scales,
yep.
Towards the end of the simulation, you said there was, the dots on the points on the two circles.
Yes.
But there were also points off the circles.
Yes.
And there didn't, might be mistaken, but there didn't seem to be any when you just had the one length scale with the one circle.
They were just lower amplitude.
Oh, they were just lower amplitude.
This is just the reciprocal
okay.
lattice vector of both those length
Okay.
scales.
And what do all those points off the scale, off the circle, represent?
They're higher order effects.
Okay.
So you're adding many of each of the length scales, and some combination, you will land up at one of these points. Yeah. And maybe I will. Can you go to the last slide of the presentation? Further back. No. As in slide of the extra slides, the last slide. I just wanted to show you the reciprocal lattice vector of the quasi pattern. Okay, sorry, we have to walk through. This is the one I wanted to show. If we are starting for a periodic crystal, the reciprocal lattice vector always goes out, but that's not the case when you have a kind of a irrationally, this dodecagonal symmetry. You start to add more and more peaks close to 0 and close to 1 again. So this is just RLV2. That's already that many contributions you have to consider. And that's what you were seeing. Some of them you were seeing in the Fourier transform. Thank you.
One more question, I think at the front.
Thank you. Thank you, Priya, for the experts in the room. Definitely kick-ass presentation.
Okay.
My question is also to do with this homotopy, but really once you've got your solutions and then you start to follow them in a different parameter, you made this comment that you said you can only change that you're going to complex, or
some of the complex solutions can become
and
real.
they can become real, and so that's how you create or lose
Yeah.
them if you want in the real space. Yeah. I was wondering, once you go into your 3D space, then there should be more possibilities of what is happening.
You mean three-dimensional patterns?
Yeah, in like the possibility of what that creates.
I mean, the dimensionality of the pattern is somehow lost when we go to the ODEs, because now it's an amplitude and a mode kind of separation. So I have maybe 2 equations or 3 equations for 3 different amplitudes. That is all that the homotopy knows. It doesn't know whether the initial pattern came from 2D or 3D. But I haven't seen anything special happen yet for the 3D continuation. It is a bit more work, but yes, I haven't seen anything yet, is all I can say. Yeah.
Thank you.
Yeah.
Thank you very much for all the questions. And of course, let's thank Priya once again for her inspiring talk.